My great pleasure to welcome you all for attending the third day course of drift-driven seismic design of buildings. The first day course, I think the first day course was an awakening call that perhaps most of us are in the wrong direction in terms of focusing on force demand rather than drift demands. The second day course introduced some simplified but effective methods of estimating periods and deformation shapes of frame structures and wall structures. And the third day course will be definitely the most amazing one. So Santiago, the stage is yours.
Thank you very much for such a kind introduction. I hope indeed today is amazing, as you said. We'll see, you'll tell me. Let's hope the computer doesn't crash today and the projector cooperates. I had to go home and reinstall a couple of programs after that big crash. That took me a while. Sorry. It took me a while to recover from that crash, which means I didn't sleep a whole lot. So when you said waking call, I feel like I need a waking call myself, wake up call. All right, so let's summarize what we said yesterday. We talked about Rayleigh's principle of conservation of energy as a simple but effective means to calculate periods and mode shapes. We also simplified the displacement spectrum this way by using PGV to estimate its slope and by drawing the relationship between spectral displacement and period as a straight line. Very simple, but again effective. When it comes to period here, what was done by Professor Sozin and his associates, starting with Shimazaki, was to calculate the period for gross sections, but increase it some. And I was trying to look for a good quote related to this thing, and I found this quote from Sozin himself in a paper from 2003. He said that factor of roots 2 there was introduced there not in expectation of the cracked section reducing the stiffness to 1/2, but instead it was introduced there because it was convenient. Mehta loved that kind of thinking. That's the paper that is titled The Velocity of Displacement, where this expression was introduced first by including that roots 2 factor there. Once we have the spectral displacement, then we can project it to the MDOF system. We can project it to any floor or any degree of freedom system using the mode shape and the modal participation factor. And that modal participation factor can be about 1.3 to 1.5. No, sorry, that's what follows here. The modal participation factor can be somewhere between 1.5 and 1.25, depending on whether you're working with frames or with walls. That is if the mode shape factor, the roof is normalized, so it's 1. Using these ideas, we can also talk about the ratio of the maximum story drift ratio to the mean or roof drift ratio, and we saw that if you have a well-configured structure with uniform stiffness, that ratio is about 1.3. If you have a soft story, for whatever reason, that ratio can be higher. 1.5 for reasonable cases, or when you really have a very tall first story, of course you're going to get more trouble. That ratio, I've seen it to be as high as 2. But if we don't play games with soft stories and whatnot, this is not a bad assumption. And then last, yeah, when we put it all together, what we realize is that the roof drift ratio can be estimated this way. PGV times T over roots 2. That roots 2 comes from the 2 in the denominator there, and the other roots 2 in the numerator. That cancels out to be roots 2 in the denominator there. Again, this is our way to project to the roof, and this is a factor that is about 1.25, 1.5, depending on what you have. You divide all that by h to get a ratio, and that's what gives you the roof drift ratio. That's essentially what Sozin said. But I'd like to go a step further, one little step further, and just say, well, you know, if this product is somewhere in this range, and if I'm going to divide by roots 2, which is clearly an approximation, you know, just a convenient factor, it's not based on physics or mechanics, it's just a calibration factor. Oh, for at least the purposes of proportioning or sizing a structure to begin with, might as well just admit that this is going to almost cancel out with that. Meaning, at least to begin the design process, I should be able to just do that. Right? The gamma and the phi 5 will almost cancel out with roots 2. So if I just want the roof displacement, I can just do that. And frankly, that works pretty well in many cases. At least when we've tried this, the correlation between measurement and calculation is pretty good. Be careful. There's always deviations, right? So say when you try to compare what you get from this versus what you get from a nonlinear dynamic analysis program, for instance, or from a test, there will be a deviation. Don't judge this on the basis of one exercise. There is scatter, right? If you judge this, try to judge this on the basis of as many data points as you can. It gives you a fairly reasonable, if maybe a little bit conservative estimate of roof drift. And if you remember the example we looked at yesterday, well, I'll go back to it in the test. Sorry, during the break, because I don't have it ready. But we can test this with a couple of examples here if you want. Questions? This is sort of a summary of what we did yesterday. Yes?
Just one. In Taiwan, we have so many faults. So there's a near fault effect, like velocity cost. So we were at a PGV very large. So this equation still stands.
Well,
for that special case.
Thank you. That's a very good question. So for the camera, in case the microphone doesn't catch that, the question is, what about near fault effects? Because in Taiwan you have many faults and you've you've measured very high values of PGV near faults, right? Does this work in that case? Well, what I can tell you is that when we've tried this equation and compared measurement versus calculation, we've tried it for a whole bunch of different records, including COVID, which I think is a near fault record. Maybe not as demanding as Chichi 1999 station 006 or whatever it was. That station where you measured that gigantic velocity of 2 or 3 meters per second. We haven't tried anything like that because no one has tested anything like that. We've always tried to judge this on the basis of measurements. So the best thing I can tell you is that for COVID, this works okay. This has maybe the poorest correlation with measurement in the short period range. When you have a building that is just a couple of stories tall, you have a very short period, that's where this thing is not, well, that's where we see the most scatter. In fact, Professor Cheng did some tests recently where we saw that this might not always give you the best result. And I wanted to address some of that here for the benefit of everyone. So these are, again, comparisons of calculation in the x-axis versus measurement in the y-axis. Okay? The calculation is done on the basis of what we've been discussing here. In this particular case, we did use the model participation factor and the mode shape factors and so on to get this the best we could. All right? But other than that, the method is the same. We're using PGV to define a spectrum and so on. And that's the correlation we see. The catch is that most of these tests were done for structures with relatively long periods. The structures within the period of, the range of nearly constant velocity in the spectrum. There are some data here within the period of nearly constant acceleration, within the range of nearly constant acceleration, but not many. That's in a way an active area of research. But what I wanted to show you is the following. You see, all this is based on what in this case Pratik Shah in his thesis called an estimate of period that he called T1. That was simply the period based on gross sections, amplified by the roots 2 factor that Shimazaki proposed. That's what he got. There's another caveat here that is not trivial, which is he didn't have in these calculations to compute the period, he didn't have rigid offset. What that means is that he ignored the additional stiffness that occurs in the beam column joint. He used center-to-center spans and center-to-center column heights. He ignores that extra stiffness that occurs at the joint. That's easier, right? When you build your model, it's easier to ignore that. So that's what he did there. But one of the questions that Dr. Shah entertained was, well, would we get better correlation if we used instead the period calculated for the cracked cross-section? In that case, it wouldn't make sense to amplify that times roots 2, right? That would be like amplifying the period twice. So what I'm going to show you next is a similar plot where here, instead of using this, I'm going to plug in the period calculated for cracked sections. Does that make sense? And what I want you to pay attention to is not so much whether the data fit the measurements better in terms of the mean, but what I want you to pay attention to is whether there is less or more scatter, because frankly that's what matters. You know, if you don't match the mean, that's okay. You can take care of that by introducing a factor, right? That doesn't matter. What really matters is whether you see more or less scatter. So let's see what we get. So again, this is what we get with periods for gross sections increased by the roots 2 that Shimazaki proposed, mostly to get a mean here that is smaller than 1. And in Lepage's thesis, the goal here was to obtain a mean of 0.8. We're getting 0.9. Not too bad. But pay attention to the standard deviation. These are statistics related to the ratio measured to calculated values. So here comes what we obtain when we use cracked sections and we ignore the roots 2. Again, that's assuming center-to-center dimensions or using center-to-center dimensions. I see a lot of people taking photos. You have all these in the Dropbox. I mean, I don't mind the photos. In fact, take more of them. but you have everything. Also, the references that I've been quoting, at least the main ones, I've added to the Dropbox too under a folder called references. But here you go. There is maybe a little bit less scattered. If you see the standard deviation is a little bit smaller, but not much smaller. You see the mean is low, maybe a little too low, meaning the period is a little too long now. Pratik Shah, Dr. Shah also wondered, well, maybe, you know, I'm reducing the stiffnesses more, increasing the period more by looking at cracked sections. And then I'm also using center-to-center dimensions. What if I assume the joints are rigid? What if I use rigid offsets? And then this is what he gets. Frankly, in my mind, in terms of standard deviations, in terms of scatter, all the solutions are fairly comparable. I mean, standard deviation of 0.3 versus 0.27. Those are coefficient of variations almost, if you realize that the means are close to 1. It's hard to get any better, frankly. And the effort that it takes to calculate cracked sections, or moments of inertia for cracked sections, is clearly larger than the effort that it takes to calculate the moment of inertia of the cross section. Number one. Number two, ideally you should be running these estimates at the beginning of the design process, right? And at the beginning of the design process, you don't quite know what reinforcement you're going to use and whatnot. And then on the other hand, we don't know the earthquake, right? And more likely than not, the earthquake is going to be different from what we expect, because it usually is. The more we measure, the more we realize that when we thought before it wasn't so. PGA, if you plot, actually I have that plot, if you plot the maximum PGA that has been measured year by year, it goes up and up and up, because we're measuring more and more. The same is true for PGV. And therefore all our probabilistic analyses of hazard and whatnot are bound to keep giving us bigger and bigger estimates of hazard as we accumulate more measurements. Okay, so on that basis, I would suggest that at least for preliminary design and the initial stages of design, this is good enough, and this is good enough even if we plug in a period for the cross section. Okay? Questions? All right. Well, I think the next question should be, again, what about strength? What about forces? Right, this is all about displacements, but there will be forces within, because the displacements are going to induce forces. And yesterday I tried to start discussing about the base shear coefficient, right? To me, that's the first thing we should check, make sure we have more than a minimum. And different minima have been offered over time, but in my mind, the easiest thing, if we're going to start using displacement or drift-based design, the easiest thing would be to comply with tradition, meet the code. Base shear coefficient should exceed SA, spectral acceleration, divided by the reduction factor, whatever it is, 3, 4, 5, 8 in the United States. And that's an easy check. But we need to get a hold on the strength of the structure first. And I started this exercise when my computer crashed and everything went the wrong way yesterday. So if you, no, that's not it. The next exercise. By the way, I printed all these MathGap documents to PDF, just in case you decided you don't like MathGap. I think you should like Mac. I think it's very convenient. If I was showing you, say, Python code here, this would be very difficult to read, I think. Or if I was showing you MATLAB code again. Or if I had an Excel file with a whole bunch of calculations, you know, in each cell, that'd be hard to read. I think this is much easier to read, and in that sense, this is much more adequate when it comes to engineering calculations. Let me make things a little bit easier to read. So if you remember, I set up this example with the same column all throughout the height of the building, the same beam, and I calculated the strength of the beam for positive moment and for negative moment using this approximation for the lever arm, because that's usually good enough. And then I also calculated the flexural strength of the column. And I did that for the column in the lower story, and I did that for the column in the upper story. And I was right there. Let me introduce some space here. Okay. I was right there when I tried to move on and the computer crashed. So let me first ask if you have questions about what I did up to that point. All right. If you remember, and I hope this doesn't crash the computer again, if you remember, what I was trying to do was to think of this mechanism where we had hinges in the columns at the base and a couple of the columns at the roof. That's where things went wrong, right? When I tried to draw a hinge here or something, then the whole thing broke down. Anyways, we have hinges at the ends of most beams, and hinges at the ends of or at the bases of the columns, and a couple of hinges at the top, like that. And what I said is I'm going to introduce a virtual displacement associated with deformations occurring only in the hinges. So nothing bends here. In this virtual displacement, all the elements remain straight, and all the deformations concentrate at the hinges. And the idea is that if I do that, all the internal work is occurring at the hinges. And internal work at a hinge is simply moment times rotation. And when I add all the products of moment times rotation, I obtain the total internal work. That should be equal to the external work, which will be the products of forces times displacements. And I'm going to assume a linear distribution of force. When I equate internal and external work, I should be able to estimate the total base shear, the total lateral force associated with that mechanism. And that's what I'm about to do here. So I'm going to say that I have this virtual mechanism. The rotation occurring in the column is going to be 1 micron, say, at the roof, divided by the height of the building. Okay, that's a rotation occurring in the column. If you ignore the size of the joint, if you assume the dimensions of everything are center to center dimensions, then the rotations of beams and columns will be the same. But if we realize that the joint has a finite dimension, it doesn't take too much imagination to see that the beam rotates more than the column. Let me try to illustrate that with a sketch, again, hoping this doesn't crash the computer. Again, the idea is it's very difficult to, well, let's see if I can. Now I gotta draw on the screen, which means I have to do this duplicate. Yeah. Okay, that's better. So if the column does this, like that, the beam has to accommodate a little bit more rotation, because the beam has to accommodate a little bit of vertical displacement here and a little bit of vertical displacement there. So if this is theta, use a different color, if this is theta, this angle here is more than theta. And you can exercise your trigonometry and your favorite high school geometry concepts and realize quickly that all you need to do to estimate beam rotation is multiply by the ratio of center to center span to clear span. That's all it takes. Easy. And this makes a difference, especially when you have big columns and short spans, or when you have walls and coupling beams. Right? Because those beams there are going to have to rotate a lot between wall segments. Okay, so with that in mind, I should be able to calculate internal work. So first, let me just say that all I'm trying to do is multiply moments times rotations. Okay. So moments times rotations, and then moments times rotation. Over here, I have moments occurring in columns. The C stands for column. The B stands for the columns in the bottom story. And the T stands for the columns in the top story. In the bottom story, I have 12 columns. Four times 3, 12. In the upper story, we said we were going to have hinges in the columns only in the interior columns, of which I have 6. 1, 2, 3, 4, 6. So that's why I have a 6 there. Remember, in those interior columns in the upper stories, I have one column fighting two beams. I'm assuming the beams are stronger because we have 2 of them. So the column might hinge there at the top. So that's why I have a 6 there and not a 12. All right. So those are the columns. And again, all I need to do is multiply moments times rotations to understand the internal work occurring in them. Now here are the beams. The beams on one side yield at the top, on the other side they yield at the bottom. So I have positive moment capacity and negative moment capacity there. The OC is slightly bigger rotation than the columns. And then the last thing I need to do is count how many beams are going to yield. Well, I have in each frame, I have 1, 2, 3 beams, right? And in each frame, I have, or in each floor, I have 3 sets of beams. So that's 3 times 3, all right? And then up the height, I have 1, 2, 3, 4, 5, 6, 7 levels that look like one another. And then the 8th level is a little different. So, again, I have 3 frames, each one with 3 beams, yielding at each end, and I have 7 levels like that. And then at the roof, things are different because, again, we think the columns might yield before the beams in the interior, but on the outside, I have 3 hinges on each side of the building. So 3 hinges with positive moment and 3 hinges with negative moment. I think that's all the hinges, if I did a miscount. And that would give me this much external work. Internal work. You realize the units are not units of energy because I multiplied or I calculated these rotations on the basis of a displacement that I called 1. Not 1 meter, not 1 micron, just 1. If I had entered dimensions of length in here, then that would give me joules, right? But no need for that. It's one nothing really. So questions about how I'm calculating the internal work? We're all good? Yeah? Okay. Now let's calculate the external work. It's not too hard. We need to define the force distribution though. That's probably the hardest thing here. That's the biggest guess, because who knows what the force distribution is going to be. And we're going to discuss that today. Every time you calculate base shear coefficient, you calculate it for a given force distribution. It's almost like if you had, say a beam. We have a beam sitting here, and if you ask me, what's the strength of that beam? I would have to ask, well, for what kind of loading, right? The strength is one thing. If you put a load in the middle, strength is different if you put two loads on it, or uniform load, so on. It's kind of the same idea. Just for the sake of argument, I'm going to assume a linear distribution of force. Forces that vary with height linearly. So I have 8 floors, and I'm going to assume that the force at each floor is proportional to the floor height. I could multiply this times h to use elevation, but it doesn't matter. What is more important though is that I make sure that my force distribution, or these fake forces if you will, add up to 1. Because that is going to allow me to do my math easier here in a second. That allows me to do the following. Let me not get ahead of myself. See, the next thing I do is I define the virtual displacements associated with those rotations I calculated before. The virtual displacements will be, well, at the roof, I would have 8 over 8, 1. And then as I move downwards, I will have smaller and smaller displacement down to 0 at ground level. So the displaced shape is just a straight line. And then, again, that allows me to do this very easily here. I multiply forces times displacements, and that gives me the external work. These are, if you will, normalized forces. In a sense, what I've done is I've factored out the base shear strength. You could argue that those are not actual, does not actually work. If I wanted to obtain work, I should multiply everything by the base shear force. What I'm doing is something we did before in a different context, which is I'm normalizing this with respect to base shear. So that's why I'm calling this relative work, as opposed to just work. And therefore, I can factor out base shear and obtain base shear by dividing internal work by this relative external work. And that gives me 2,000 kilonewtons. Of course, base shear is best expressed in terms of total weight, so this was the weight that I assumed for each of the floors. So in terms of base shear coefficient, I obtained that. And if you guys remember, when I ran Stera yesterday, I don't have it open. I'll open it in a second. But if you remember, when I ran Stera yesterday, I obtained a base shear coefficient a little bit beyond 10%, maybe 11% or so, when I did the so-called pushover analysis, right? So, there you go. You can check your calculation, your sophisticated calculation by hand with arithmetic. All you need to do is imagine a mechanism and calculate rotations, products of moments times rotations, products of forces times displacements. It's fairly easy once you get used to it. I gave you a chapter from our book that explained these step by step, and it also explains something interesting and important that I should not forget. what you should be asking me is, how do you know this is the right mechanism? Well, I don't know. That's just my first guess. What you should do next is try other mechanisms. What are other mechanisms? Well, we could have a mechanism that looks that's 1, 2, 3, 4, 5, 6, 7, 8. We could have other mechanisms, for instance, where we have only hinges in one floor. Say top and bottom of each column like that. That's a story mechanism. It would deform something like this. Yeah, it would deform like that. Right? With all the deformations happening in that story. That's another plausible mechanism. There are many plausible mechanisms. You could have another mechanism where you have hinges maybe at the bottom of the columns and maybe at the top of some columns here with hinges in the beams in between. Let's draw that just to make sure it's clear. We could have another mechanism where maybe we have something like this. So 1, 2, 3, 4 columns. And 1, 2, 3, 4, 5, 6, 7, 8 beams, and then the idea is that you could have hinging here, here, and here. Maybe you have hinging there, 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 and there, and then in between you might have hinges and beams like that. That's another plausible mechanism that can happen. That mechanism would deform probably like so. Right? There are many possibilities. Which one governs? Well, you know how nature works. A chain breaks at the weakest link, right? Nature somehow figures out the worst possibility. I don't know why. Why does that happen? So nature will find the weakest mechanism somehow, and that's what governs the strength of this thing. And just try one. More likely than not, the mechanism that would govern a building like this would be something like that, a partial height mechanism. Very difficult to get a full structural mechanism all the way up. Very, very difficult. Unless you've been playing games and you have maybe many partition walls up here and none here, or you have a very tall first story because you want big shops there and so on, you know, that shouldn't happen. And here's a place where we do need to worry about hinging and internal forces and so on. I mean, when we say displacement is what matters the most, that doesn't mean we need to ignore what goes on in the structure in terms of forces. Because clearly we want to avoid this. So you want to run your either so-called pushover analysis or do what I'm showing you here and make sure that this doesn't happen. Make sure that whatever you do to the structure, however you distribute the reinforcement, whatever dimensions you use, lead to something like this, or even better, something like that, with as many stories hinging or yielding as possible, right? That's the goal. And try to avoid this. We try to avoid mechanisms with maybe yielding in, say, 2 stories only. That can happen too. By and large, if you have a wall, this is very unlikely, right? If you have a wall all the way to the foundation, right? This is very unlikely. If you have a wall all the way from foundation to the roof, even this is unlikely. when we have walls, more likely than not, we have something like this. Because in this context, a wall is nothing but, you know, sort of a very fat column, like that. And more likely than not, it's going to yield at the bottom, right? And not yield at the ends or the bottom and the top of one story. That's very unlikely. You can do the math. You can see if you have a wall, you can try to see if that type of mechanism governs. Seldom does. So here's one more reason to use walls. They will spread the deformations better and get you out of this type of trouble. Okay? So those are at least two reasons why you do need to look at forces and hinges and mechanisms and so on. The first one is, again, you obtain a base shear coefficient, an estimate of base shear coefficient, like we did here. And this you should compare versus sort of established consensus, which is compare that versus SA over some sort of reduction factor. When you do that, you might want to use effective weight instead of full weight, but let's not get sort of hung up on that. This R factor is so large that little tweaks on the actual weight to use there don't matter too much. But compare the base shear coefficient with what's required by tradition. That should get you out of trouble. Oh, why can't I tap? Don't crash again. So that's one reason to look at hinging and mechanisms and but not. The other reason is that you want to make sure that when the structure becomes nonlinear, it does so not to concentrate deformations in one story, but to sort of spread the joy. Yes. Because this, of course, is going to create very large drifts. Just one single story that's going to get you in trouble. Questions so far? I'm sure we have this first break, 40 minutes. Maybe in a few minutes we'll have the first break. But I want to introduce the next idea, which is related to this. See, another beauty or another neat thing about this type of analysis is that it helps you realize sort of the worst condition that could occur, say, in a beam. That is the condition in which two ends yield. For a case like this, you would argue that the worst condition that could occur in a column is when the column yields top and bottom. And for a wall, the worst condition that could occur in terms of high forces occurring in these elements, the worst condition that could occur in a wall would be one in which the wall yields and the elements connected to it also yield. Right? Once you realize that, understanding the magnitude of the internal forces occurring in the building is a matter of statics. Very easy. Quite a relief. Because you don't have to deal with dynamics and, as they call them, time histories of anything to find the worst forces that could occur in your beams and your columns and your walls. All you need is statics and the realization that eventually things are going to yield. And if we want to prevent shear failures or bond failures and so on, what we need to look at is the conditions of equilibrium for that state where things are yielding. Because that leads me to the next topic. What are the worst forces that occur in an element? I see I'm still duplicating things. Don't need to do that. Extend. There we go. Here. There we go. So, what's the worst thing that can happen to beams, columns, and walls? What are the peak demands in terms of internal forces that can occur on this thing? So let's start with beams. Again, if I have a frame like this, when I have only gravity in a beam like that, the conditions of equilibrium would be related to that kind of free body diagram where I probably have negative moments at the ends causing tension at the top, and then of course shear like that. The issue is that when the earthquake occurs, the ends are going to yield. When one end is going to yield, causing tension at the top, and the other end is going to yield, causing tension at the bottom. Meaning those moments, one of those moments is going to reverse and become positive moment, like that. And when you look at it that way, you realize that because of that, there will be additional shear in the beam. If the gravity load and black here produced always upwards reactions like that, the moments which now sort of add up to one another, the two moments have the same direction, if you will. The two moments require a counteracting couple that comes from the reaction, and that translates into extra shear. That extra shear would simply be the summation of the end moments divided by the clear length of the beam. Let's write that down, just in case. If this is the moment capacity, or here we have to be careful. You see, here's where more is not better. The stronger the beam is in flexure, the higher these end moments will be, and therefore the worse the shear will be. So we need to be conservative by assuming the materials are stronger than they might, than you might think. What I mean is, we don't want to calculate here the nominal capacity of the beam. Where's the mouse there? We don't want to calculate the nominal capacity of the beam. We want to calculate the probable capacity of the beam. Meaning, we need to assume, for the purposes of estimating the extra shear we're getting here, we need to assume that the yield strength of the bars is going to be higher than it says on the piece of paper there, that it's just the nominal strength of the beam. So we need to calculate this for a higher yield stress. And we have to do that here for negative moments, and we have to do the same here for positive moments. So this will be the probable moment capacity. I can draw a little circle there. I'll try again. Control Z doesn't work. All right, well, whatever. That's a P. And then where's the mouse? There it is. Then this will be done for positive moments. And again, you have to be careful there in the sense that once you realize that being conservative here means calculating a high number. If you're looking at tension at the top, you need to include not only the bars in the beam, but maybe also bars in the slab that might help resist negative moments there. This, of course, if this is W, say for ultimate loads, for factor loads, this will be W L over 2. Very difficult to draw this thing, L over 2. Whew. Whatever happened to the times when we just used the blackboard? And I got the same over here. Same. Yeah, same over there. And then over here, this shear, extra shear, should be the summation of the moments, probable moments, P, for negative and positive moments, quite the exercise. Couldn't go for a run this morning, but this is making up for that. And then I divide by the clear, or if you will, the net span, the span from face of column to face of column. That's the extra shear that we get in the beam. You guys know who said that first? You guys know who first realized, oh, I don't even need to know much of dynamics, or I don't even need to know what the earthquake is going to be like to calculate the worst shear that the earthquake can induce. I just need statics and the realization that the beam is going to yield at each end. Do you know who said that first? Meditzosen said that first in the book written or published under the names of Bloom, Newmark, and Corning in 1961. That was the first instance of capacity design. This is how this was called later, mostly by the Kiwis, I think. The Kiwis coined the term, the New Zealanders coined the term capacity design, which became very famous around the world. This is very convenient. So the Kiwis get the credit all the time for capacity design. But Michael Fardis wrote a paper recently in maybe engineering structures, where he dug the origin of capacity design. Capacity design was introduced in New Zealand thanks to what appeared in the book by Bloom. It turns out that Bloom was written by several people, one of them being Sosen. Sosen wrote the chapter where this shows up. Okay. So that's what happens in column and beams. In columns, we have something similar and more. Let me first start with the exterior column. The exterior column, of course, has axial load that is related to the shear in the beam caused by gravity. I wanted to draw a circle there. So there's axial load in the column that is delivered to the column mostly through shear in the beam, right? That's what I'm trying to illustrate there. But we just said the shear in the beam is going to increase, right? That's what we just said here. The shear in the beam is going to increase. This upwards reaction in the beam is downwards force in the column. That means I have extra shear in the beam like that, which becomes extra axial load in the column. So the first thing we need to admit is that because of earthquake, the exterior column is going to see more axial force. Of course, this is what would happen if all the beams yield. As we just discussed, it's unlikely that all the beams will yield at the height of the building. But if they do, that's what would occur. So the axial load would be higher. A column in the middle, like this, that would have the same additional shear from the beams on each side, except that one is pointing up and the other one is pointing down, so those cancel out. So this extra axial force occurs at the end of the frame, but not in the middle. Nevertheless, now that we're talking about the middle, what I'm saying is, if I have extra shear from this beam like that, I can draw an arrow. Yeah. Then I have extra shear from the next beam going like that, and those cancel out. As opposed to the extra shear here at the end, which doesn't cancel out with anything. The same can be said about extra shear occurring here, which would subtract from the axial load, but again doesn't cancel out with anything. But while we're at it, we might as well admit that that column is going to see moments. The moments are going to have opposite signs, because we're looking at a deformed shape like so. No, I got that wrong. The opposite deformed shape. Not like that. I have tension on the left side. I have a deformed shape like that. Yeah. Almost like so. And then, of course, the opposite at the bottom. But that picture is now in equilibrium until I add shear like that. That's the shear that would be induced by the earthquake, and the worst condition would be the one in which the column yields top and bottom. So the maximum shear that can occur in a column because of earthquake would be the summation of the moment capacities, which are usually the same at the top and bottom usually. So twice the moment capacity divided by the column height. That's the worst shear that can occur in a column. 2 MP, the probable moment capacity for the column, divided by the clear story height. That's the worst shear that can. I wanted to write clear, but that's not going to work. Well, imagine that says clear. That's the worst shear that can occur in the column. Questions? What I want to do next is look at the worst condition that could occur in a wall. What's the worst shear that can happen in a wall? That's going to be trickier. So why don't we take our first break now? Yeah, maybe we start again at 20 past the hour. And went to more or less like this. How do I handle force transfer from frame to wall? How do I deal with that? Should I be thinking about relative stiffnesses and things like that, or what do I do? So here's my suggestion. Yes, the wall has this type of deformed shape, and the frame has this type of deformed shape, so they kind of fight each other. They make a good marriage, but in every marriage there's a little bit of a fight back and forth about, all sorts of issues from cooking to cleaning. It's kind of the same thing with these things. They kind of fight each other, but at the end, together they work quite well. The idea is, especially here at the top, the frame pulls the wall back, or the other way around. The wall tries to pull the frame along. So the diaphragm, the slabs, are going to have to transfer forces between them. Slabs and beams, the floors will have to transfer forces between them. How high are those forces? Easy. Run your pushover analysis or your limit analysis and look at this free body diagram. Cut your wall right above a given floor, cut the wall right below the given floor, compare the shear values above and below. The difference between those two shear values is that whatever force is coming through the floor, right? From the frame or from whatever. That's the force that you're going to have to transfer. So you don't really have to worry about relative stiffnesses or anything like that. You just run your pushover analysis, your limit analysis, and from the statics of the structure in its limit state, once things have yielded and so on, from that you can estimate almost every force you are interested in within the structure. Does that make sense? Sir? Does it make sense? When you think force-based design, that's when you start thinking about, oh, do I need to worry about relative stiffnesses and so on? In a way, that doesn't make sense. I know that's how we operated for many years, but in a way that doesn't make sense, because in the earthquake, the structure is going to yield. And once things yield, relative stiffnesses don't mean anything. Right? If you read chapter 7 in the book on drift-driven design, which I gave you, you'll see examples of structures that were designed following force-based design and linear analysis based on relative stiffnesses, right? And then structures that were not designed that way at all. And those structures were tested with the same earthquake. There was a very specific example of a structure with two coupled walls. And they designed the coupling beams again using linear analysis and thinking of stiffness and so on. And they got certain reinforcement ratio for those coupling beams. Turns out linear analysis called for very high reinforcement ratios. Okay. And then they did a parallel test in which they put 4 times less reinforcement in the coupling beams. And they shook the two structures. Made no difference. And I just went to more or less like this. How do I handle force transfer from frame to wall? How do I deal with that? Should I be thinking about relative stiffnesses and things like that, or what do I do? So here's my suggestion. Yes, the wall has this type of deformed shape, and the frame has this type of deformed shape, so they kind of fight each other. They make a good marriage, but in every marriage there's a little bit of a fight back and forth about, you know, all sorts of issues from cooking to cleaning. It's kind of the same thing with these things. They kind of fight each other, but at the end, together they work quite well. The idea is, especially here at the top, the frame pulls the wall back, or the other way around. The wall tries to pull the frame along. So the diaphragm, the slabs, are going to have to transfer forces between them. Slabs and beams, the floors will have to transfer forces between them. How high are those forces? Easy. Run your pushover analysis or your limit analysis and look at this free body diagram. Cut your wall right above a given floor, cut the wall right below the given floor, compare the shear values above and below. The difference between those two shear values is that whatever force is coming through the floor, right, from the frame or from wherever. That's the force that you're going to have to transfer. So you don't really have to worry about relative stiffnesses or anything like that. You just run your pushover analysis, your limit analysis, and from the statics of the structure in its limit state, once things have yielded and so on, from that you can estimate almost every force you are interested in within the structure. Does that make sense? Sir? Does that make sense? When you think force-based design, that's when you start thinking about, oh, do I need to worry about relative stiffnesses and so on? In a way, that doesn't make sense. I know that's how we operated for many years, but in a way that doesn't make sense, because in the earthquake, the structure is going to yield. And once things yield, relative stiffnesses don't mean anything. Right? If you read chapter 7 in the book on drift-driven design, which I gave you, you'll see examples of structures that were designed following force-based design and linear analysis based on relative stiffnesses, right? And then structures that were not designed that way at all. And those structures were tested with the same earthquake. There was a very specific example of a structure with 2 coupled walls. And they designed the coupling beams again using linear analysis and thinking of stiffness and so on. And they got certain reinforcement ratio for those coupling beams. Turns out linear analysis called for very high reinforcement ratios. Okay. And then they did a parallel test in which they put 4 times less reinforcement in the coupling beams. And they shook the two structures. Made no difference. And that just goes to show that linear analysis doesn't really help much if the structure is going to yield. Okay.
Question.
Yeah.
How large the force will be transferred from the diaphragm to the shear wall is dependent on the how you simulate the floor diaphragm. If the floor diaphragm is very stiff,
right,
the force will be a large force will transfer to the shear wall. So it depends on how to model the diaphragm.
That's true. Yeah, my recommendation is try to bracket the answer. Assume rigid, assume flexible. I'm guessing with rigid you're going to get much more force transfer, right? See if you can accommodate that. in my experience, that's not too difficult, especially if you have beams that can help you drag the force into the wall. I did work in a project or a high-rise 60-story building in Bogota, Colombia, where the transfer of forces became quite tricky. It was very difficult, but that's because the diaphragm was full of openings around the core wall. Yeah. The other thing I'd like to say is when you have sufficient wall, when you have wall Chilean style, walls everywhere, the force transfer is very simple because you have so much contact between the diaphragm and the walls that, yeah, it's seldom a problem. The force transfer is seldom a problem. The other thing I like to say is that I don't know if you saw different things in Chichi in '99, but in every earthquake I've been to, I've never seen a cast-in-place system, diaphragm, that fails and causes a big collapse. Cast-in-place. Precast, that's a different story. Did you see cast-in-place slabs in trouble in Chichi? Yeah, I haven't seen it on. So, the force transfer somehow works, even if you don't do the math carefully. But there's a way to do the math. Okay. Where were we? Yes, we were talking about this. See, my mind is still struggling with your question. Because it would seem to me in limit analysis, once things are yielding, even the relative stiffness of the diaphragm is not necessarily critical. Because once things are yielding, the structure is essentially determinate. You know the internal forces. They are related to the strength of the columns and the walls and so on. So I don't think it's so critical to define the stiffness of the diaphragm.
Just as you mentioned, in some cases the floor diaphragm is not so rigid. So the assumption of rigid floor diaphragm could not be applied to some cases.
Yeah, but let's imagine I have maybe I have a system like this. Say I have sorry, I need to do the magic here again. Like this. Okay, let's say I have a floor plan like that. And let's say I have a big shear wall here and a big shear wall there. And just to exaggerate, let's imagine we have a frame in the middle. Like that. About how much stronger the columns have to be to avoid yielding in them before yielding in beams. And boy, it takes a lot. I've seen people recommending the beams have to be 3 or 4 times weaker than the columns to ensure that you never get a plastic hinge in a column. You'll find plastic hinges in columns, even if you try hard to avoid it. So in my mind, do that, but still design the column so that it can yield top and bottom, just in case. I know the shear forces related to yielding top and bottom in the column are high, but it can be done. Do you do that here? You assume the beams yield. And when you do that, include the contribution from the slab on the strength of the beam. Because that's when it gets tricky, right? Because the slab makes a big difference, and the question is always, how much of the slab is helping the beam? And that's a tough one. So I prepared this. I understand. Okay, so let's talk about walls. Because walls are a little trickier. I showed this video yesterday. In fact, let me show you that same video through a different PowerPoint that I have here, which is a little bit more comprehensive. Where did it go? NTU 2025, peak demands, and then this presentation is just about shear in walls. There we go. Shear in walls. So I have the same video here, but before I go there, how often do we find walls in trouble because of shear? Well, it does happen. But here's a picture from Chile after 2010 by Patricio Quintana. That looks like a shear failure to me in a wall in a building in Chile. But that was rather uncommon. Most of the walls in Chile had mostly compression damage or something that looked like compression damage concentrated near the base. Or sometimes you had things like that. That's very hard for me to call. Is that a shear failure or something related to compression or something else? But there was a lot of this, sort of a single section with a lot of concentrated damage. But this wasn't common. Sort of a clean, clear shear failure. That was hard to see in Chile. By and large, I would say most walls in Chile, and we talked about this, most buildings in Chile are full of walls, and most of those walls did very well in shear. Not so well in bending, but in shear they did well. And we're going to talk about why they didn't do so well in bending. In shear they didn't do too well. However, there's been a lot of research on shear demands in wall buildings. Let's talk first about measured shear demands, and then we're going to talk about sort of expected or calculated shear demands. Let's talk about observations, measurements. So in tests like these, which were done by Sozen and Urbana and described in chapter 7 of the book, in tests like these where they had, and in this case, a frame, two frames, one and two frames, connected to a central wall. In frames like these, they could mount accelerometers at each level. They knew very well the mass of each level. And by adding mass, or by multiplying mass times acceleration, they could get estimates of inertial forces at each floor. Like that. And once you have estimates of inertial forces at each floor, you can calculate base shear and overturning moment, right? It's not too hard. In fact, I hope we can do that with our building in Tainan next week. The caveat for our building is when we have torsion, the acceleration is going to be different in different parts of the floor, and the mass is not uniformly distributed, so we need to think about which acceleration we multiply by each mass. These guys didn't have that problem. The mass was uniform, the acceleration was the same in each floor, so they had it easy. And what I'm going to show you next is what they saw when they plotted force along height for buildings like this one. There you go. These are plots of forces along the height. These are floor inertial forces. Those are forces occurring when the base shear was maximum. Okay? What do you see there? I see a mess. I see that sometimes the force distribution resembles the shape of the first mode, the crosses here, right? And sometimes it seems to resemble the shape of this, where's the second mode? Yeah, maybe this is a combination of the first and the second mode. I don't know. It doesn't quite go back. I don't know if it's because they normalized. But the bottom line is that you don't always get the shape of the first mode in the force distribution. And the force distribution can be quite different. And that means that the resultant of the forces is not always up high. The resultant of the forces can be quite low. Right? And if the wall is going to yield at its base, the maximum shear will depend on where those forces are applied, right? Where the initial forces are applied. If they're applied up high, then you need little shear to develop the full flexural strength of the base. If the shear is applied down low, then you're going to have to apply much more force to develop yielding in flexure at bottom. So that's an issue. We don't know where the inertial forces act, so to speak. We don't know where the resultant acts. And there's been a lot of work on this. Here is work done by Mark Eberhard, who now works at University of Washington. Let me see if I can explain his plot here. All the dots refer to measurements from 3 different test series, tests like the ones I just described. The y-axis refers to the maximum base shear that was measured in the tests, just like I said, multiplying accelerations times the masses and adding them up, divided by the maximum calculated shear, calculated by using limit analysis, assuming distribution of forces resembling the distribution of the first mode. Okay? So 1 means you get the right shear using the first mode or something similar to the first mode. That's what 1 means. But the data show that you usually get more shear, right? Depending on, if you will, the intensity of the earthquake. The more intense the earthquake, the higher the shear. That's what this means. And it exceeds what you would expect from the pushover analysis. Trouble, right? If you calculate the maximum shear at the base on the basis of a force distribution that doesn't necessarily resemble the first floor, the first mode, but instead you use the force distribution measured in the test, then you get it just right. That is, if you knew the force distribution, the shape of the force distribution, you can get the shear just fine using limit analysis, mechanism analysis, push-up, whatever you want to call it. So the mystery here is essentially what's the distribution of inertial forces that gives us the right shear. Well, let me show you again this video. In a tall building dominated by a wall like this. These are aluminum walls, but for our purposes, they help illustrate the same idea just fine. Yeah, the displacements are dominated by the first mode. But the forces may not be dominated by the first mode. You see, if you notice at the beginning of the shaking, the second mode is kicking in there, right? And you can see it's shaking with high frequency, of course. Right? High frequency usually means But high acceleration. And those accelerations are going to be high somewhere here, and maybe towards the top too. Because the shape of the second mode is something like that. A belly and then it kicks back. That is to say, the second mode can introduce high accelerations and therefore high inertial forces at locations where you wouldn't expect them on the basis of the first mode only. So first mode dominates displacements, but it doesn't dominate forces. Not completely, not as in displacements. In those tests with those aluminum Mickey Mouse shear walls, when we calculate the base moment, because again we had accelerometers at each mass or on each mass, and we could multiply mass times acceleration and do statics to obtain the overturning moment. If we plotted moment versus top displacement, we see, of course, the structure is linear to begin with, but eventually it starts to yield, and the moment at the base didn't quite flatten completely, but the increase in moment after some displacement here became much, much less than what was happening over here. The thing yielded, right? And therefore that caps the maximum moment that occurs. However, when you look at acceleration at the top versus displacement, you don't see that flattening effect, so to speak. The acceleration keeps going up and up and up. The basic idea is that the first mode could cause yielding at the base, but the second mode and the other modes are beyond the second mode don't necessarily cause yielding. So the more you shake the thing, the higher the accelerations associated with those higher modes, because you don't have yielding associated with those. The more you shake, the more things accelerate. Here's again a plot of inertial force versus height. Once more, sometimes you get a distribution that is like that, almost triangular, or at least something resembling maybe the first mode, but sometimes you get the second mode in there superimposed on the first mode. That's why this doesn't kick back, because this superimposes the first and the second mode. But clearly the second mode has a big effect on the inertial forces sometimes. And that's why when you plot base shear versus top displacement, you get a mess like that. Right? You don't get a nice hysteretic loop, you get that mess, because the second mode is changing the lever arm of the forces, in essence. And this is what this plot shows. The y-axis shows the relative location of the resultant of the inertial forces in that spaghetti-like building with 17 stories. That is, say, if I had a uniform distribution of force, the resultant would be at mid-height, here. If I had an inverted triangle, the centroid of the lateral forces will be at a third from the base. If I have a triangle that peaks at the top and is zero at the bottom, then I'm at 2/3 over there. So what this shows is that the resultant of the lateral forces can be, somewhere out there as high as 80% of the height of the building, but sometimes it's as low as 30% of the height. Those lateral forces can be really, really low, the resultant of that. And that's what gets the shear wall in trouble. It's just as simple as the idea that if I want to open that door and I want to push from the handle, I have an easier time. But if I want to push closer to the hinge, I need to apply more force. It's the same idea with shear walls, and that's why when you plot base shear versus moment, you don't see a linear relationship. You see that the base shear can increase much, much faster than the moment does. So, yeah.
So like when you calculate the, let's say the previous figure, this height, so you have a distribution of the lateral force.
Measured.
Yeah, measured, and they occur at the same instance. Right?
Yes, of course.
Okay, so let's say for one shaking table test, one ground motion time series, like you can take different time step and all do this kind of
Right.
Not just take the one associated with the maximum drift or
Yeah.
okay.
Right.
Same thing for the calculation of the moment.
Right.
Okay.
So, what does the profession do? Well, what do you guys do in Thailand about this? Oh no, you don't use shear walls, so you don't have this problem.
No, we follow ACI, so we have omega V.
Okay, well, so let's talk about ACI. And ACI went through a code cycle that ended in 318 in 2019, where many changes were introduced. And unfortunately, some of those changes had to be undone, at least to some degree, in the next cycle of the code, which just ended. So let's talk about what we thought we knew until 2019, and let's talk about what is being done now, because it's different. So in 2019, this idea was introduced that you can calculate the shear on the basis of linear static analysis, but of course that's going to give you probably an underestimation of shear. So they say you need to amplify that by two factors. The first factor has to do with the fact that the structure has to yield. The wall will yield. So the product of this omega, let's call it this overstrength factor times V sub u, the product of that is simply supposed to give you the shear associated with yielding at the base for probable moment. So omega times BU, you can just use, instead of that, you can use limit analysis like we've started here, push over, and get your shear from that. That's all. You would have to use probable capacities, right? So an increased yield moment and so on. So this product in my mind is fairly clear. I could replace the product with, say, V sub P, probable shear, done. Or if you will, probable moment divided by roughly 2/3 of the height, done. That's not hard to justify. What is harder is this omega factor, which the ACI code will tell you is there to account for the higher mode effects, which is just a fancy way to say that factor is there just to correct the lever arm, right? Well, until recently, that correction factor had this shape. For slender walls, because this doesn't really affect short walls, for slender walls, they give you this for the omega factor. It was a function of the number of stories. And for shorter buildings, they penalize the shear less. For taller buildings with more than 6 stories, they penalize the shear more. And they almost duplicated or doubled the shear because of higher mode effects, or to account for the fact that the resultant can be lower. You could argue that an amplification of 2 is consistent with the idea that instead of having a force at 2/3 of the height, you might have a force at 1/3 of the height. That ratio is 1 to 2. 2. You could argue that's consistent with observation. But lots of engineers complain. They said, oh, this is too much shear, we can't design, blah, blah, blah. So 318 sort of gave in and said, well, it's true, we don't see a whole lot of shear failures out there, at least in Chile where we have so many walls. We don't see very many shear failures. And it is also true that these forces are happening, these high shears are happening very quickly, and they might have to do with force distributions that we seldom use in the lab. When we test that wall in the lab, we usually don't apply a whole lot of forces in different directions. We usually just apply one force at the top. And then to make matters worse, in the lab, we seldom have the floors connected to the wall. We just have the wall. And if you think of the floor and how it interacts with the wall, you could argue the floor and the beam are gigantic stirrups that help control shear. So there were many reasons to backpedal. So ACI backpedaled. They went backwards. And essentially they said, oh, okay, stop complaining. The omega factor for overstrength that stayed the way it is, you can just calculate the moment capacity of the wall and use that to obtain the maximum probable shear. The big change was related to the amplification factor for dynamic effects or higher mode effects. The big change had to do with the idea of lowering the height of the resultants. And they changed the variable from number of stories to height. I don't know why, but they did. And they gave this new equation that is based on height. So what I've done is I've plotted the two equations, the old one and the new one, for you to compare here. There you go. Yeah. There is as much, in my mind, there is as much engineering in this change as there is politics. Yeah. Because I try to sort of eyeball an average of the increases implied by the new equation. Now it's 25% increase on average, at least up to 30 stories or so. That's not as bad as the 100% increase, or well, 80% increase that we had in 2018. So we really backpedal a lot, I think. Well, what works better in terms of observations? You saw this before. This was a work by Eberhard, where all these dots represent measured shear forces. Eberhard working again with Metasozen. I don't know how Metasozen managed to do so much in life. Unbelievable. This is wrong here for me. Okay. You hear me okay? All right. So Eberhard and Mark and Mette decided just to draw a straight line here to fit this data and say, well, that straight line tells you how much extra shear is going to occur. It's going to be a function of PGA, they said. And if you look at what that gives you compared with what you measure, this is data from all these tests. And this is the ratio of measured versus calculated shear, calculated as Eberhard and Sozen suggested. You get a pretty reasonable upper bound, or let's say a pretty safe upper bound. What they suggested seems fairly conservative. And it just comes from this plot, which will suggest that you calculate your shear on the basis of a mechanism analysis, and you add, I think it is 30% of this product. That doesn't. Yeah, that's about right. They say if you want to know how much extra shear there is, calculate the shear, you always do with limit analysis, and add 30% of the product of PGA and W. Easy, very easy. That seems to work okay. It's fairly conservative based on the data we have of measured shear. 318.19, also fairly conservative. 318.25, reduce this a lot. 318.25 will be somewhere here. So, I'll leave it up to you. I'm not going to take responsibility for this. What I would suggest is simply, remember, when you do your limit analysis, you always do your limit analysis for an assumed force distribution. That is assumed. The actual force distribution will be different. If you want to be safe, change the force distribution. Lower the centroid of that distribution. Lower the location of the resultant. How far? Well, you tell me how far you want to go, how conservative you want to be. But the measurements indicate, again, the resultant can be as low as 1/3 of the height. All right. That's on the side of demand. What about capacity? And I think Professor Wang has very good ideas that he can offer to all of you, better than I can. Let me just say that the ACI offers this equation to speak of the shear strength of the wall, where in PSI units this value can be 2 or 3 depending on aspect ratio. And this is, of course, the contribution from the reinforcement, and this is the contribution of the concrete to shear strength. And when we compare measured versus nominal capacities calculated this way, this is what we get. This was work by Merve Usta at Purdue University. This is calculated shear strength. This is measured shear strength. Our methods to estimate shear strength are fairly conservative. You measure more than you calculate. And again, these are walls tested in the lab without the benefit of the gigantic stirrups that come in the shape of slabs and beams that will restrain any inclined crack that tries to cross the floor level. I don't think we have enough data about that kind of wall. You were telling me that they're having some tests in Japan, maybe?
Japan, and currently I think UCLA, they have more than 1,000 test data. For sure.
With the beams and the slabs?
You mean with the diaphragm?
Yeah.
Probably not many.
Now that's, because I think if we're going to be this conservative, or this conservative, if we're going to lower the resultant to 1/3 of the height, we might not want to be also ultra conservative when it comes to capacity, right? And what I mean is maybe we need to examine the capacities of walls with diaphragms that confine them. But I'll leave it at that. What I want to do next is show you an example. Because I want to show you that even when I use sort of nominal properties, and even if I remove the resultant of the forces very far down, I think I can still make a wall work. So unless you have questions, let's put some numbers to this. Okay? Okay, so here are my numbers again. You have these. If I haven't been able to convince you that math is good, don't worry, you can read this in PDF. But this example comes from the book on drift-driven design. The example is a full example of the design of a building, starting with an architectural drawing like that, and talking through estimates of drift, talking about how much wall this thing should have, all the way to detailing issues. It's a full example within reason. We wanted things to fit within one chapter in the book. I'm going to be concentrating on one of these walls, like that. I want to design a wall for shear. Okay? And in fact, that's done in the book. But here I changed a couple of things just slightly, just for the sake of argument. But the wall in elevation looks like that. It's a wall within a frame, so to speak, like you were saying, Professor Wang, yesterday. And again, you asked this question yesterday. With the approximate method I showed you to calculate period and mold shape, would it work for this type of wall? Yes, it does. And there's a reference in the reference folder that shows how the formula works. But let's not talk more about period and mold shapes. I think you've had enough of that. Let's talk about shear for this wall. All the columns in this building look like this. 750 by 750 with 12 D28s for longitudinal reinforcement and fairly generous transverse reinforcement. That's what the columns look like. The boundary elements in sort of Japanese style are the same as the columns. Okay? That's what the Japanese do. They usually don't use rectangular walls. They use infill within the frame to create a wall. So this wall has a dog bone shape cross section. Okay. So remember that 12 D28s and each boundary element, again, which looks like a column. The length of that wall from center to center is 8.5 meters. The height of the building is 3.35 meters times 7. You'll see that through the book and most of the examples, most of the buildings are 7 stories tall. That's because Sosen always liked the number 7. He thought it was a lucky number. He liked to insert jokes in his work like that all the time. All right, so this is a boundary element that is, of course, monolithic with the web. The web has this much reinforcement. The web has D12 bars, 2 layers at 250 millimeters, and the thickness of the web is 350. Not too stingy, but not Chilean style either. You know, the Chileans have 50 centimeter walls. So I think there's room to increase that if needed, but I think I made the numbers work out okay with that thickness. Yield strength, concrete strength. I was very much tempted to make the concrete strength 36, so I can take the root of that easily and obtain a 6. It looked a little funny. Okay, so that's your building. Okay, we're going to design one of these walls for shear. So the first thing I'm going to do is I'm going to try to calculate the moment strength of the wall. And I'm going to do that in approximate fashion, like I did yesterday, for another wall, I think. And then I'm going to show you sort of an accurate, rigorous calculation, or the result of that. Again, the boundary element has 12 D28s, so that's the area of reinforcement and tension on one side, one boundary element. I take that area, multiply it by the probable strength of the steel. Do you use 1.25 times Fy here too? In New Zealand they use 1.35. But then they don't use a phi factor when they do this kind of thing. This is what I was telling you last night, Professor Wang. Why do we do these things that's slightly different in every country? So engineering is starting to look more and more like a religion, you know, something you believe locally. Anyway, so we have force in the boundary element times arm. And I'm going to take the arm to be the distance from boundary element center to boundary element center. Easy. That gives me the contribution of the boundary element reinforcement to moment strength. Then I have the axial load, which I calculated on the basis of tributary area. It's that much. And it should contribute this much to the moment capacity. Force times arm. And the arm, I'm assuming, is half the distance from the center of the section to the boundary element. All good? Very easy. But then, of course, I have the web reinforcement too, the vertical web reinforcement that can also yield and contribute to the strength. So in the web I have 2 layers of D12s. and they are spaced at 250 mil. This is the clear distance from column face to column face. So I have this many layers of 2 bars each. So this is just total area of vertical web reinforcement from here to here. Total area of web reinforcement. This is the strength. And the arm, again, I'm going to assume is half the length to the center of the boundary element. Everyone with me? Yeah? Pretty easy, sort of static. I get a moment capacity of 80,000 kilonewtons meter. I'm not doing D over D minus A over 2, or I'm not drawing an interaction diagram or anything like that. I know the axial load is below the balance point, and for that condition, this is fairly good. And if you don't believe me, here's a moment curvature plot for this section. This is 80,000 kilonewtons meter. Pretty good. This moment curvature plot was computed with all the bells and whistles and, you know, a parabolic distribution of stress in the concrete and all that stuff. Okay, so I know the probable flexural strength of the wall. So you would think that from here on it's just a matter of taking that moment, dividing it by some lever arm, and you get the shear, right? Why not? Well, it's a little bit trickier than that, because when you look at that wall carefully, this is the example that I said we have in the book, with more numbers that you probably want to see. But if you look at that wall carefully, in its limit condition or in its limit state, yes, the wall will yield at the bottom here, and we know the moment capacity at the bottom now, 80,000 kilonewton meter. And it will yield, of course, under the action of some lateral forces with a resultant at a height that we can debate for the reasons we said, but the beams are likely to yield as the wall is rotating, right? So the beams will probably apply their moment capacities at the end too, and also shear forces. So the overturning moment created by that lateral force is resisted not only by this moment here, but also by all these other moments, and these couples created by the shear forces. But if I assume the beams are yielding, I should be able to estimate these shear forces easily, and these moments the way we already discussed. If I know all these moments and shear forces, finding the shear here is just a matter of statics. Right? Very easy. So I do that, and I do my statics, but I'm going to spare you that. And I conclude that because of the beams and the moments they apply and the shear they apply, the actual overturning moment capacity can be 50% higher than what I calculated. That was your question yesterday, Professor Wang, right? All right. So now I'm ready. I know the overturning moment capacity. I can divide that by some arm and get the shear. So the first iteration I did here was to say, well, I'm going to assume that the resultant forces are at half the height of the building. Just for the sake of discussion, that is to say, I'm going to assume the lateral forces are uniformly distributed. That gives me this as the height to the resultants. If I calculate shear, therefore, by dividing moment by arm, I get a base shear of, what's that? 10 million newtons. Is that a lot? Sounds pretty high, 10 million newtons. 10,000 kilonewtons. Yeah, maybe it's high, maybe it's not. I strongly recommend we talk about shear, as in most other cases in engineering, in terms of stresses and not absolute values like force. So I'm going to divide that by the nominal shear area, which I am going to obtain just by multiplying web thickness by wall length from side to side, including the boundary elements, and divide shear by shear area, and I get a stress of 3 megapascals. That's a lot easier for me to digest because I was told by Medesosen many times in earthquakes, or when you're dealing with earthquakes, try to keep the shear to less than 6 roots F prime C in PSI. In megapascals, that's 6 divided by 12, half roots F prime C. I'm there. It's not great, but I'm there. You know, the code will let you go higher than that. You could design this to assign all the shear to the ties and ignore V sub C. But if you don't want to ignore V sub C because that might be too conservative, and again, if we admit that the beams are going to force the inclined crack to have a fairly shallow angle, then maybe you could argue that V sub C could be this high. I'll let you try different values, but in a way, just for the sake of argument, I'm going to assume V sub C and PSI units is as high as 3 roots F prime C because I have shear panels that are fairly squat. In megapascals, that becomes 3 over 12, that's 1 over 4. I'm going to assume that's V sub C. If that's V sub C, then the reinforcement ratio I need is obtained by subtracting from the total shear the contribution from the concrete. That should be the contribution from the steel. This 0.75 here is a strength reduction factor. The shear stress associated with the steel divided by the strength of the steel with the strength reduction factor gives me the reinforcement ratio. This is the transverse reinforcement ratio required to resist this shear with web reinforcement. If I put two bars on each layer of the number 5, and that's, you know, good transverse reinforcement. I have a 9-meter wall, you know, 350 thick. I should not be too stingy with the transverse reinforcement. If I have number 5 at 150 millimeters, that gives me a reinforcement ratio of 0.75% or so. That should be enough. Doable. If you want to lower the resultant some more, we can. So here I went with a very low resultant at 1/3 of the height. So of course the shear increases. That's almost 8 roots F prime C and PSI, 3/4 in megapascal. That's getting high. But hey, I've been very conservative here, right? That's fairly conservative. And I think that's one of the problems that has been giving us trouble here. We're maybe being too conservative in too many steps. We're sort of piling up too many factors of safety. But so if I'm okay living with this much shear stress, I do the same exercise and obtain a required reinforcement ratio now for ties in the wall of 1.1%. I can provide that with the same D16s, but 100 millimeters. And that's heavy, but it's doable. If you think that's too heavy, just increase the thickness of the wall. And I think you can make that work. Does it make sense? So, Professor Wang, you're the one who brought this up. Maybe on the first day you said one of the reasons why engineers in Taiwan don't want to design shear walls is that it's very difficult to handle the shear. Yes, it is kind of difficult, but at least in my experience and with this sort of perspective, It can be done. What do you think?
Probably our structure and the span too large and quite a few for shear wall. That's the reason it turned out that demand is pretty high.
The walls are very long.
Right.
Oh. That maybe.
Because our engineer also checked using the ACI strength equation, and it turned out that about 60, sometimes 80 centimeter for thickness. And then they run into trouble with the architect.
Yeah. I can see an architect complaining about that. Yeah. Well, I think we do need to look at tests from walls with diaphragms. See what we get from those. Because my suspicion is that you probably get much higher shear. Especially if you have a very long wall relative to the story height, right? Each of the panels, wall panels between floors really has a low aspect ratio. Yeah. So maybe a prestigious international research institute such as maybe ENCRE could do some tests and maybe help the profession that way and show that maybe there's more shear strength than we think.
Right. And I think the one way is consider the actual load. The actual load is helpful,
right?
For current shear. Why not for wall shear?
That's right. No, it should help. And also, do we really need to be this conservative, right? I don't know if the engineers here have tried the new equation, but it does lower the demands quite a bit. Because I don't know if we need to operate at a very low bound here. A third of the height, doubling the shears is fairly conservative. I feel like we could allow some points below a line here. Again, I think we're maybe being too conservative in too many places. And then what gives me peace of mind is that I look at the buildings in Chile and you don't see shear failures everywhere. So, okay, questions? Because we only have half an hour left, right? We're supposed to end at 12. We've taken only one break, right? So maybe we can, sorry, losing track of time. Well, why don't we take our second break now? We start again at 30 past the hour, and then I'll try to finish with the topic of drift capacity. Okay? Thank you. Yeah, sorry to give you just a short break, but I don't want to run out of time with this last topic. So, Professor Huang, you were telling me that you couldn't find some of the files I was using here. I just discovered that Dropbox had stopped syncing my files with the cloud, probably because of the crash yesterday. So, but it's syncing again, so you should be able to find the files. See, they're all going up.
Okay.
Okay. Now they're going up fast now. Look at that. All right, so let's wrap up with this discussion. You see, so far I've talked a lot, maybe too much, about drift demand. Then we talked about internal forces that can occur after the structure yields and so on. But the one topic that we still need to talk about some is drift capacity, right? And the sort of earthquake equation of drift-driven design, there is drift demand on one side, and there is drift capacity on the other side. Now I want to start this discussion with a quiz. Everyone included, even professors. So imagine you have a beam like this, 12 inches or 30 centimeters deep or 15 centimeters wide. That's what, 9 feet long, so 3 meters or so long. Imagine you have reinforcement at the bottom, of course, and then what we're going to do is we're going to vary the amount of the reinforcement we have at the bottom. So in some cases we're going to put a lot of reinforcement, in some cases we're going to put much less reinforcement. Okay? Simple exercise. Then we're going to plot moment versus curvature for the different amounts of reinforcement, and this is what we're going to get. So for a beam with a lot of reinforcement, you get a moment curvature diagram like this, and as we reduce the amount of reinforcement in the beam, then we get, of course, less strength, but we get more curvature to the limit. The limit would be the limit associated with a strain of 0.003 or something like that. Okay, so here's the quiz. Which of these beams, these 6 beams, if you were to test them in the lab, which of these beams will be able to achieve the largest deflection? Come on. Professor Chen? Beam R02. Who won? Of course, by now you know I'm asking a trick question, because that's sort of the obvious answer. But it turns out that if you said that, you're wrong. These are, in essence, load deflection curves for these beams. Yeah. The beam with less reinforcement was more brittle than some of the other beams. Of course, the beam with a lot of reinforcement also ran into trouble. The beam with a lot of reinforcement runs into trouble because you crush the concrete too early. The beam with too little reinforcement gets into trouble because you find fracture occurring at a single crack. Right? You're very familiar with the idea of minimum reinforcement, right? This is a sort of a deep beam, or rather a wall turned sideways, that was tested by Ash Puranam, who you know. And this thing had essentially minimum longitudinal reinforcement, distributed as you would have it in a wall. And when we tested this thing with Ash, I hope the volume is not on, yeah, it's kind of annoying. So we were applying a single force in the middle. We had rollers at the end. Very soon in the test we get a crack in the middle like that. No surprise there. What is more interesting is that as we keep pumping and increasing the force in this rod, you don't see more cracks. You see just that one crack getting wider and wider until eventually the thing goes running. Yeah, we're pumping, and eventually, boom, all hell breaks loose. Beams and walls with minimum reinforcement or less than minimum reinforcement are very brittle because all the curvature concentrates essentially a single section. You see, this beam might have a large curvature capacity, but curvature doesn't do you any good unless you can distribute it over a certain length. And that's the problem here. So that's one challenge that we face when we try to calculate the deformation capacity of reinforced concrete. Strain concentration happens and it's very difficult to quantify its effects. Strain concentration causes load deflection curves for that wall tested by Ash that look like this. This was initial cracking. After that, this thing couldn't recover. Essentially, the reinforcement cannot compensate what is lost when the concrete cracks. What I usually tell my students is, if you're not going to put more than the minimum reinforcement, do yourself a favor, don't put any reinforcement in the structure. Save that money because you're gonna need it to pay your lawyer. Might as well make the structure out of glass. So that's challenge number one in relation to calculating deformation capacity of elements. Here's challenge number two. I think everyone in the room is probably familiar with a picture like this. In this case, this picture refers to the curvature distribution that we expect for a moment diagram like this, which is what you would get when you have shear and moment in an element like that. The idea that was first proposed in 1954 by McAllister working with Chet Sees at Urbana. Chet was a co-advisor of Meta Sozen together with Nate Newmark. Very nice guy, super nice guy. Anyway, bright too. Chet essentially was the one, as far as I can tell, who came up with the idea that there is a region here where the plasticity spreads. Right? He's the one who came up with the plastic hinge analogy. And the length of this region where you have a lot of plasticity is of course called the plastic hinge length. Right? You're all familiar with that, I assume. That's in every book and in many papers. And the essence of it is that the maximum deformation you could achieve in, say, a beam would be the summation of the yield deformation plus the extra curvature that you get past yield times the plastic hinge length. Curvature times length gives you rotation. Rotation times arm gives you deformation. Most of us, when we went to school, we were taught this is how you calculate the deformation capacity of something made out of reinforced concrete, like a wall. Turns out that doesn't work. These are snippets from a paper written by Toshikatsu Ichinose, Professor Ichinose, formerly at Nagoya Institute of Technology, who did tests with Susumu Takahashi. And they were looking at walls like this one with a boundary element on one side and no boundary element on the other side. This happens in Japan sometimes when the architect wants a door here, so they cannot connect the web to the next boundary element. And they were wondering what's the deformation capacity of this thing. And they noticed that the deformations in the concrete and compression tended to concentrate in a very small area. The deformations concentrated in an area of height here that wasn't anywhere close to what we usually assume. We usually assume, on the basis of tests of beams, that the plastic hinge length is D, the effective depth, or D over 2 maybe, right? Somewhere there, long length. Well, that might happen maybe on the side in tension, but it doesn't happen on the side of compression, sorry. And this picture shows how much the deformation is concentrated in their specimens. And if you've seen pictures from buildings in Chile surveyed after 2010, they all look like that. Deformation is concentrated on the siding compression in very short regions. And Takahashi and Ichinose proposed in this paper that the height of this region is not related to D or to the length of the wall, but it's mainly related to the thickness of the wall. So Ichinose says thickness is more important than confinement. And for that reason, it's good to have an enlarged boundary element, right? Not a thin boundary element. Bottom line is that this equation doesn't work very well for walls, especially when you have load cycles. The equation was derived for beams under monotonic load. When you apply this equation to walls subjected to cycles, this is what you see when you try to plot calculation versus measurement. A mess. No good correlation at all. This was work done by Ying Wang and again Ash Burana. So because of this, because of what happened in Chile, because of what Takahashi saw, people have been trying to find ways to spread the plasticity in the compression zone. And these are images that show cross sections that were tested by Carlos Arteta with Jack Maley at Berkeley in 2014. I happened to be there because I was there on sabbatical, my previous sabbatical, 2014, more than 10 years ago. And I saw them struggle to try to confine elements that they were testing in compression to try to spread the plasticity in the concrete in something resembling a boundary element. But no matter what they tried, almost in every test, the deformations were concentrated in a fairly short length. Long story short, the plastic hinge analogy doesn't work very well when we want to calculate deformation capacity of walls. And that's why in the ACI code now you find equations like this one. This is a regression. This is sort of a confession that we don't know what's going on. Right? This is just, in this case, what's his name? Abdullah. I'll remember his name, sir. Abdullah worked with John Wallace at UCLA. They essentially tried different parameters or ratios that seem to have some physical meaning in the behavior of the wall, and then they just do statistics. They do linear regression. They try to compare what's measured with these parameters, and they fit curves to the data. They are not the only ones who've done that. I must confess I did that in my master's thesis because I was given a homework where I was supposed to provide or calculate the displacement capacity of columns. And I couldn't do it. And when I was running out of time, I said to myself, the best I can do here is just a simple regression. And I submitted that as my homework to Professor Sosa. And I thought he was going to give me a D. I thought he was going to flunk me. Instead, he was actually quite happy with my homework. And he gave me an A, and we wrote a paper, and I don't know. But it may be one of the first papers where we used linear regressions and left mechanics on the side to calculate drift capacity. Very few people cite that paper, which is a relief because it's an embarrassment in a way, right? It's a confession that we don't know what's going on. Other people looked at the idea and said, oh, maybe that's what we should do, and then they proposed better regressions, and so they get all the citations. I don't have a problem with that because, again, it's kind of embarrassing to confess that we don't know what's going on and we have to use regressions. Things get worse, I'm afraid, because this regression actually works pretty well. But it works pretty well within a certain domain, like most regressions, right? If you go outside that domain, it doesn't work so well. This regression was fit to test data from walls without lap splices at the bottom. When you don't have a lap splice, this image here shows strain contours for a wall with this type of reinforcement, and this strain contour was obtained for a drift ratio of 1.5%. These are recent tests by Charlie Kirby at University of Canterbury. So when you don't have a lap splice, you see nice spread of the plasticity on the side of the wall in tension. On the side of the wall in compression, again, you see big concentration of strain. No surprises there relative to what Takahashi saw. These are all measurements, not calculations. But then Charlie, oops, went the wrong way. Charlie also tested walls with lap splices. And then what happens is, you still have concentration of strains in the side in compression, but then now we also have concentration of strains on the side in tension. Because the lap splice stiffens this area. You cannot yield the bars in sections where you have twice as many bars because of the lap splice. They yield and concentrate at the ends of the splice. More so down here because you have more moment, but also there's some concentration of strain at the upper end of the splice. And that's trouble. Again, curvature doesn't give you the benefit of deflection unless you can spread the curvature over a certain length. We don't have a plastic hinge to speak of here anymore. My corny joke here is that instead of a plastic hinge, we have a plastic hinge. You didn't like that one, huh? When I moved to New Zealand, I showed them this and I said, hey guys, we gotta do something about this. The Americans already banned the splice. They don't let you splice the bars at the bottom of the wall. You guys in New Zealand, you're still lap splicing the bars at the bottom of the wall. And they said, it's okay, Mike. Because we don't put all the splices at one level, we stagger the splices. So that must be better. I said, I don't know, let me think about that. Couldn't figure it out, so we did some tests. Got worse. Got worse because now you're stiffening a longer length, a longer height, and the concentration of strains is even worse. And that leads to a lot of trouble. These are pictures of two walls. This one has a staggered lap splices. That one doesn't have any splices. That one has couplers. Good couplers though. Not any coupler. I know in Taiwan you had trouble with couplers before. I've seen photos of couplers that have failed in Taiwan. But anyways, if you use a good coupler, the best coupler is the one that can break the bar away from the coupler. That works very well. Remy Lequen tells me he just tested a whole bunch of walls with, if I understood, all the commercially available couplers he could find in the US, and they all work better than a wall with lap splices. Anyways, even if you use couplers, don't put them all in the critical section, right? Why would you? The point is that we keep getting surprises when we look at deformation capacity of elements. This plot shows the deformation capacities of walls with different staggered patterns, different amounts of confinement. This is what Charlie tested. This is what we assume in design in New Zealand for the type of wall we tested, and this is what we got with couplers. Every wall where we lap spliced the bars had lower drift capacities, lower than expected, and lower than what you get without the lap splice. And that's why in ACI 318, 19, and thank God ACI 318, 25 too, this didn't get backpedaled. It took a lot of effort to get into the code. A lot of, let's call them discussions. In ACI 318, you're not allowed to put lap splices in these orange areas in the elevation of the wall. In a cross section, you're not allowed to put lap splices in this section. What do you do in Taiwan? Same. Thank God. Okay, that's walls. How about columns? Because you don't use walls, you use columns and beams and so on. What about the drift capacity of columns? Oh, I don't know why I have an extra plot there. I don't like that. Let me get rid of it. I don't know where it came from. Oh, I have 4 extra. So many, why? Okay. Sorry. What about columns? To make my story short, I'm just going to tell you that if you read the chapter from our book that I gave you on drift capacity, you'll see we evaluated 4 different methods to estimate drift capacities of columns. We evaluated them on the basis of measurements. That's what you see in the y-axis. The x-axis is what you get from these different methods. Mostly regressions, again. The first one there, method 1, is that regression that I submitted as a homework to Professor Sosa in my master's. None of them works very well, right? It's very difficult to calculate drift capacity. That expression at the top, though, again, I don't think it's any better than all the other regressions. The only thing I like about it is that the data tend to be above the one-to-one line. So I made this summary slide where I give you sources. And this is our paper that we wrote with Mede and Julio Ramirez. That's that equation that you saw there as method 1. Oh, I got an extra A there because I inherited this from a presentation in Spanish. And sorry, that's that expression that I just showed you for columns that I called method 1. And then I'm giving you here other expressions. If you ever want to calculate drift capacities of other things, this is an expression that was proposed by Usta. Before I move on, let me explain each term just to make it sure. R is reinforcement ratio, transverse reinforcement ratio. Fy is the strength of the transverse steel. Vmax is the maximum shear associated with yielding of the column, if you will. In terms of stress, A over D is of course the aspect ratio. That's this expression that gave us these numbers. That's for columns. For RC walls, I think the simplest expression out there is this one by Usta, which simply uses the A over D ratio to calculate the drift capacity of walls that don't fail in shear. Of course, Wallace and Abdullah have a much better expression that I just showed you, but if you want to run a quick number, this is actually not a bad guess. In these two cases, I wouldn't go beyond 3 or 4%. It's very difficult to get a column or a wall to go beyond 3 or 4%. Algan showed, and I'll show you the data here in 2 slides, I'm almost done, the partitions in general, whether they're made out of drywall or gypboard, as they call it in New Zealand, whether they're made out of concrete block or clay tile, partitions don't do very well if you go past 1%. They essentially get destroyed after 1%. Thin walls have this propensity to buckle out of plane. Yet another issue. Jack mainly and a Chilean researcher by the last name Parra proposed some very interesting formulation. They proposed a limit to prevent the buckling out of plane of thin walls on the basis of strain in the steel. I thought working with strains is very difficult because, as you've seen, to go from deformation to curvature is already difficult. So to go from deformation to strain is even more difficult. So I took their formulation with ash again, and we provided a limit in terms of drift instead of strain. And the idea is that a thin wall could drift more or less depending on its ratio of thickness to unbraced height. And I gave you a paper that describes how we arrived at that expression. It's on the references folder. And then last, I thought I should mention this expression that Jack proposed years ago. That's in the ACI code, and I'm guessing Professor Huang may have done some of the initial tests that fed into this equation, which says that the ability of a flat plate column connection to accommodate shear has to do with the ratio of gravity shear to shear strength for punching shear. That's in the ACI code. So these are sort of some of the ideas that are out there in the literature as to how to calculate drift capacity of things. But frankly, after devoting much of my life to trying to estimate drift capacity of columns, beams, and so on, at this point, my take is I'd rather not calculate drift capacity and depend on that. I'd rather limit drift to a low value and use good detailing. If I'm going to make a wall, regardless of the drift demand, if I'm in a place like Taiwan or a place like New Zealand, where earthquakes are so threatening, I'd rather use the best detailing possible. So in this case, I wanted to show you this to submit to you the idea that you want confinement like that doesn't depend on cross ties in the boundary. Maybe outside the boundary you might want to use cross ties because they're easier. And the other thing I would suggest is that you want these bars to be anchored in the core. You don't want lap splices here, at least not in the first floor. Put them somewhere else or use couplers. And try to restrain every bar laterally. If you do these things, and you limit drift, I think a structure has a good chance of survival. Now, how much should we limit drift? Well, again, I mentioned that the partitions tend to get damaged very early on. And this is a very powerful plot that was produced by Algan in 1982, I think. This is story drift. This is something he called damaged intensity. The idea is 1 means the partition is destroyed, you might as well replace it. There's so much damage in it that you might as well replace it. And 0 means, of course, a brand new partition. And he looked at data from tests of partitions of all sorts. You have what he called veneer, which is gypsum board or drywall partition. He looked at bricks, concrete block, clay tiles, and then those are all these symbols up here. And what he saw, to make my story short, is that if you go 1%, your partitions are going to be heavily damaged. If you have good detailing, I'll be very surprised if you have a beam, column, or wall that cannot get to at least 1%. When Algan asked back in the 80s, a group of international researchers and practitioners, what should be the drift limit to make sure that buildings have a chance to be reused after earthquakes and won't get into too much trouble. Most of the people they interviewed say, look, about 80% or 75% of the people they interviewed, they said the limit should be less than 1%. So there is some international consensus about that. So on the basis of all this, I think the best way to go about dealing with drift is to keep it low. How low? This low. If we want to save the partitions for the design earthquake. In some countries they've gone up to 1.5%. That might be okay, at least maybe that can be something that is negotiated, but limits higher than that, 2% as they use in the US, 2.5% as we use in New Zealand, I think those are limits that are too liberal. Even if you manage to convince your practicing engineers to limit the drift to 1 or 1.5%, I still think that, at least in key locations, you should use the best detailing you can, regardless of how much deformation you expect, because you never know. The earthquake can be more than you think. It often is, right? Then I can show you data again for how estimates of earthquakes keep increasing over time, again and again and again. But let's leave it at that. That's my last slide, and that's all I have to say. And look at that, it's 11:59. Thank you very much.
I think just as I said at the beginning of today's course, today's course is the most amazing one because Santiago shows how to deal with the most challenging issue of the wall structures, the walls demands and capacities. And I think all of you and all of us, including myself, benefits a lot from the 3-day short course. And I hope in the future, maybe Santiago can give us a long course instead of short course. I agree. Okay, and before the closing of the 3-day course, I would like to invite Professor Huang to give us a closing remark.
Okay, thank you, Dr. Lee. So I would like to show my appreciation for Santiago to spend such a long time and share his knowledge with us. Indeed, it opened a new vision for us, about the drift control. I think that in Taiwan, our drift control, we need to do more effort. Yeah, because due to the latest large earthquake last year in Hualien, So we can see that in some area in the west coast, away from the epicenter, but we still have some damage for our non-structural elements such as infill wall. And this infill wall occurred near the elevator and indeed caused a lot of trouble. So I think that this is a kind of urgent need. Maybe our society, we need to do something. Yeah. But change probably gradually. But anyway, we can still keep our design profession, the way the daily work we have, but we need to consider how to control the drift. I think that this short course indeed inspires us on this. So I would like to show my appreciation again for Santiago and for anchoring and generously offer this kind of environment, and we can have very good, comfortable and for the last few days. And the last is thank you all the attendants, your patience, and I think that we all learn a lot. Let's take a big pause and go.
Thank you all. Thank you.
Thank you very much for the kind words. And all the organization, all the help getting here, help with the U-bike, water, coffee, amazing. Your hospitality is just overwhelming. Thank you very much. I do have to say, for the students, I need to give them a homework, right?
Right.
So, I'm going to send you to one of you through email an exercise. It shouldn't be too difficult. My idea is to help you build a little model in Stera 3D. That's only so that you can check your numbers for the model, say for a 10-story building. I would ask you to calculate drift for a given earthquake and maybe base shear strength. And again, you should be able to check your answers for periods and so on using Stera 3D. So I hope that's within your reach. Would that be okay? No, not too difficult, I hope. I think I have to grade that homework, right? As long as your answer is reasonable, I'm not going to penalize you too much for little details wrong that may be wrong here or there. Okay? If you have questions, feel free to contact me through email. I give you my email in the first letter. Good. Thank you again.